Probability of the union of independent events. Now, as you progress in your study of probability, you will frequently run into scenarios where you aren't just looking for the chance of a single thing happening, but rather, you need to find the probability that at least one event out of a group of independent events occurs. In mathematical terms, when we talk about at least one of these events happening, we are looking for what is known as the union of those events. Now, it is important to remember that there is a general addition rule that works for any type of event. However, when we are specifically dealing with independent events, meaning the outcome of one doesn't affect the other, we can actually use a much more efficient and elegant formula involving what we call complementary events. Over the next few slides, I will show you how we move from the general rule to this much simpler method, and how you can apply it to solve complex problems easily. Welcome, everyone. Today, we are going to explore a very important concept in probability, the probability of the union of independent events. The general addition rule. Now, before we dive into the specific shortcuts for independent events, let's take a moment to ground ourselves in the fundamentals. Let's recall the general addition rule, which works for any two events, A and B, regardless of whether they are related or not. If we want to find the probability that event A occurs, or event B occurs, or even both occur, we use the formula. The probability of a union B equals the probability of A, plus the probability of B, minus the probability of an intersection B. Now, you might wonder why we include that subtraction at the end. In this formula, the term intersection B represents the probability that both events happen at the exact same time. When we add the probability of A and the probability of B together, we are actually counting that overlapping middle section twice, once inside A and once inside B. So, we subtract the intersection to correct this and avoid double counting the overlap. Keep this general rule in mind, because in the next slide, we will see how this formula simplifies beautifully when we know the events are independent. The case for independent events. Now that we have recalled the general addition rule from the previous slide, let's see how things change when we have a specific condition: independence. When we say that events A and B are independent, it means that the occurrence of one event has absolutely no effect on the probability of the other occurring. In this specific case, the probability of their intersection, which is the probability of both events A and B happening at the same time, is simplified significantly. It is simply the product of their individual probabilities. In mathematical terms, the probability of intersection B equals the probability of A multiplied by the probability of B. Now, let's take this special property and plug it back into the general addition rule we just looked at. If we substitute the product of the individual probabilities in place of the intersection term, our formula for the union becomes much more specific. We get the probability of a union B equals the probability of A, plus the probability of B, minus the product of the probability of A and the probability of B. This version of the formula is a great stepping stone, but as we will see in the next slide, there is an even more elegant way to calculate this using complements, especially when we are dealing with more than just two events. The complementary approach, at least one. Now you might be thinking, the formula we just looked at on the previous slide works perfectly fine, so why do we need another one? Well, while that formula is mathematically correct, it becomes incredibly tedious and messy as you add more events. Imagine trying to calculate the union of 5 or 10 different events using that method. It would be a nightmare. Instead, I want to introduce you to a much more elegant and efficient approach using the concept of complements. Think about it this way. The event where at least one of A or B occurs is the exact logical opposite, or the complement, of the event where neither A nor B occurs. In other words, the only way to avoid at least one happening is if none of them happen. Let's walk through the step-by-step derivation together so you can see how we arrive at this shortcut. First, we look at the complement of the union of A and B mathematically. The complement of a union B is equal to a prime intersection B prime. This is just a fancy way of saying the opposite of A or B is not A and not B. Second, because of this relationship, the probability of the union, which is P of a union B, can be calculated as 1 minus the probability of the intersection of the complements, written as P of a prime intersection B prime. Third, here is the crucial part where we use what we learned in the previous slide. Since we are assuming events A and B are independent, their complements, a prime and B prime, are also independent. This means the probability of their intersection is simply the product of their individual probabilities. So, P of a prime intersection B prime equals P of a prime times P of B prime. Finally, when we substitute this back into our equation, we arrive at our simplified, powerful formula. P of a union B equals 1 minus P of a prime times P of B prime. To summarize this concept, this formula tells us that the probability of at least one event occurring is simply 1 minus the probability that none of the events occur. This is going to be our secret weapon for the example coming up in the next slide. Real-world example. Imagine a scenario where we have two students, Rahul and Priya, both working independently to solve a complex mathematics problem. We are given that the probability of Rahul solving the problem is 0.7, and the probability of Priya solving it is 0.5. Our goal here is to find the probability that the problem is solved, which, as we discussed in the previous slide, is mathematically the same as saying, at least one of them succeeds. Let's walk through the solution step by step. In step 1, we start by clearly identifying our given probabilities. Let's define event A as the event where Rahul solves the problem, so the probability of A is 0.7. Similarly, let's define event B as the event where Priya solves the problem, meaning the probability of B is 0.5. Next, in step 2, we move to the complementary approach we derived earlier. Instead of looking at success, let's look at the probability of failure. We need to find the probability that Rahul does not solve the problem, which is the complement of A, written as P of a prime. We calculate this by subtracting 0.7 from 1, giving us 0.3. Then, we find the probability that Priya does not solve it, which is the complement of B, or P of B prime. Subtracting 0.5 from 1 gives us 0.5. Now, in step 3, we apply the efficient formula for the union of independent events that we learned in the previous slides. We want to find the probability of a union B using our formula. This is equal to 1 minus the product of the probabilities of the complements. So, we take 1 minus the quantity of P of a prime times P of B prime. Plugging in our numbers, we get 1 minus the quantity of 0.3 times 0.5. Finally, in step 4, we perform the arithmetic. Multiplying 0.3 by 0.5 gives us 0.15. Subtracting 0.15 from 1 leaves us with a final result of 0.85. To conclude, the probability that the problem is solved by at least one of the students is 0.85. Now that we have understood the theory and the derivation of the complementary approach, let's put everything we've learned into practice with a real-world example. As we move to the next slide, I want you to pay close attention because I will highlight some common pitfalls where students often trip up when solving problems exactly like this one. Common mistakes to avoid. Now that we have seen how to apply the complementary approach in our example, I want to pause and discuss some common pitfalls. Even when you understand the logic, it is very easy to fall into certain traps during an exam. First, watch out for confusing the union with the intersection. A very common mistake is to simply multiply the probability of event A and the probability of event B when a question asks for the probability of at least one event occurring. Please remember the distinction. Multiplying the probability of A and the probability of B gives you the intersection, which represents the probability of both events happening. However, if you want the union, the probability of at least one, you must use the formula 1 minus the probability of a complement times the probability of B complement. Second, never ignore the independence condition. The shortcut formula we just derived, where the probability of the union equals 1 minus the probability of a complement times the probability of B complement, is only valid if the events are independent. If you encounter a problem where the events are dependent, you cannot use this shortcut. Instead, you must revert to the general addition rule, which is the probability of A plus the probability of B minus the probability of an intersection B. Finally, be careful not to forget to use complements by simply adding the probabilities together. Some students might just calculate the probability of A plus the probability of B. This approach is only mathematically sound if the events are mutually exclusive, meaning they cannot possibly happen at the same time. Being mutually exclusive is a very different concept from being independent, so always check your conditions carefully. Keep these distinctions in mind as we move to our final summary of the key takeaways. Key takeaways. To wrap up our lesson today, let's review the key takeaways to ensure you have a solid grasp of this concept. First, I want you to remember the at least one rule. This is your most powerful tool when dealing with independent events. Whenever you encounter a probability problem that asks for the likelihood of at least one event occurring, don't feel pressured to calculate every possible successful outcome. Instead, take the shortcut we discussed in slide 4. It is almost always much easier to calculate the probability that none of the events occur, and then simply subtract that value from 1. Second, let's look at the formula itself. For any two independent events, A and B, the probability of their union, which we write as P of a union B, is equal to 1 minus the product of the probabilities of their complements. In mathematical terms, that is, 1 minus P of a prime times P of B prime. This is the streamlined version of the addition rule we looked at earlier. Finally, let's reflect on the underlying logic. This formula isn't just a random shortcut. It is mathematically derived from the fundamental principle that the complement of at least one is none. By finding the probability of total failure and removing it from the total probability of one, you are left precisely with the probability of at least one success. Keep these points in mind, and you'll find that even complex probability problems become much more manageable.